Hello and welcome to week 4 demo assignment for the program Deep Learning Part 1. So the first question is, what is all required to choose a different learning rates for different weights? The given options are to avoid problem of diminishing learning rates, to avoid overshooting of optimum point, to reduce vertical oscillations while navigating the optimum point, or option number D is this would aid to reach the optimum point faster. And the correct option is option number D, that is this would aid to reach the optimum point faster. Let's understand why. In case of adaptive learning rate, the learning rate will be reduced for parameters with high gradient and learning rate will be increased for parameters with small gradient. This would aid in reaching the optimum point faster, and this is the benefit of choosing different learning rates for different weights. Question number 2 is RMS prop resolves the limitation of which of the following optimizers? Option A is ADA grade, option B is momentum, option C is both A and B, and option D is neither. The correct option is option number A, ADA grade optimizer. Let's see why. RMS prop tries to resolve the ADA grade's radically diminishing learning rates by using a moving average of the squared gradient. It uses moving average instead of simple average. It utilizes the magnitude of the recent gradient descents to normalize the gradient. It uses recent gradient descents only. Okay. Hence, it solves the ADA grade's limitations. The question number 3 is, which of the following statement is true? The first is gradient update rule of momentum optimizer and NAG are same. Okay, gradient update rule of momentum optimizer and energy natural accelerated gradient are same. Option number B is momentum optimizer and NAG optimizer performs differently irrespective of the learning rate. Option number C is possibility of oscillations is lower in NAG than momentum, and option number D is none of the above. The correct option is possibility of oscillation is lower in NAG than momentum optimizer. Let's see why. We can view NAG as the correction factor for momentum optimizer. NAG is seen as a correction factor for momentum optimizer. If the velocity added gives a high loss, then momentum method can be very slow, as the optimizer path taken exhibits large oscillations. But in case of NAG, if the added velocity, which is used to calculate intermediate parameters, leads to bad loss, then the gradient will direct back towards the last position. It will go to the last position, and hence this helps energy avoids oscillations, and hence possibility of oscillation is lower in NAG than momentum optimizer. Question number 4 is gradient of particular dimensions point to the same direction, that is gradient and parameter directions are same. Then what can you say about the momentum parameter gamma? Choose the correct option. The first option is the momentum term increases. Option number B is the momentum term decreases. Option C is cannot determine or cannot comment, and option number D is it remains the same. The correct option is gradient of particular dimension points to the same direction, then momentum term increases. That is, gradient is same direction as the points, then momentum increases. Let's see why. Let's take an example. When we push a ball down a hill, the ball accumulates momentum as it rolls down. It gets faster and faster as it reaches to the downhill, becoming faster and faster on the way until it reaches its terminal velocity if there is an air resistance, that is gamma less than 1. The analogy is same for the parameter updates, and thus option number A is correct. That is, whenever gradient is in the same direction, the momentum term increases. The last and fifth question is, ADA grade has its own limitation. Can you choose that limitation from the following options? Given options are accumulation of positive squared gradients in denominator. That is one of the possible option. Option number B is overshooting minima. Option C is learning rate increases, thus hindering convergence and cause the loss function to fluctuate around the minimum or even to diverge. Option D is getting trapped in local minima. The correct option here is that Adair's has a limitation that accumulation of positive squared gradients in the denominator. Let's see why. Accumulation of squared gradients in denominator is a problem as every added term is positive, thus accumulated sum keeps growing during the training. Okay, the denominator keeps growing during training. This causes the learning rate to shrink and eventually become infinitely small, which is not desired. We don't desire something like that. So the correct option is accumulation of the positive squared gradient is really a limitation of Adair because it shrinks the learning rate to 0. So that was it for this particular demo assignment. Hope it helped. Thank you everyone.